Welcome back to yet another video. Today we are going to talk about solubility and then we'll finish up with colligative properties. And for your sake, I hope you're not missing colligative properties in class, because if you're missing that in class, you're missing ice cream, and that's just sad. So we will start with solubility. Last video we started talking about molarity. Okay, we were talking about different concentrations. So we're still kind of on that whole idea of talking about solutions with our discussion today of solubility. Solubility is exactly what it sounds like. It's the ability of a solute to dissolve in a solvent. So how well is something able to dissolve? The way we measure solubility is it's really in terms of the amount of solute, how much of the powder. And again, you know it doesn't have to be powder. I just use that because it's easier to visualize. So how much of the solute will dissolve in a given amount of solvent. It is not an endless process. Okay, so let me finish writing this. Given amount of solvent. This is not endless. If you have a glass of unsweetened tea and you start putting sugar in it, there comes a point where you cannot get any more sugar to dissolve. No matter how much you stir, it is actually full. So that's what we're getting at. In your PowerPoint, I have got a list of all sorts of solubility rules. When you take higher level chemistry, you start learning that there really are rules about what dissolves and what doesn't. For example, nitrates are all soluble. So if you've got sodium nitrate, potassium nitrate, all of those are going to dissolve. The rules get a little more complicated when you get to your carbonates and your phosphates, your hydroxides. So you can look over those, but you do not need to know them. What you need to know at this level is very simple. It's the idea of like dissolves like. Generally with us, the way we look at solubility is we look at polarity. Polar substances tend to dissolve in other polar substances. That's what I mean by like dissolves like. Polar will dissolve in polar. Non-polar tends to dissolve in non-polar. Now that is not an absolute rule. That is just a general kind of concept we follow. Because the degree of polarity totally matters. Something that's really, really polar, really strong positive and negative sides, and then something that's not so much, it's not going to be as easy of a mixing. So just keep in mind the basic premise of like dissolving like. With that comes two new vocabulary words for you. The first one is the word miscible. If you see miscible, miscible are actually liquids, okay, that are completely soluble. Lots of times we think of solubility and dissolving, like I said, as a solid into a liquid. But it's not always that, okay? Water and alcohol, for example, are completely miscible. It's how people will make Jell-O shots, for example. It's actually what liquor is made of. You have a mixture of water and the alcohol, and they stay completely mixed together. They don't separate. You don't have to stir them, okay? The flip side of that, this is your other word, is immiscible. Immiscible are liquids that do not mix with each other, okay? So we're really focused kind of on liquids here, all right? So these do not mix. Most common example, you probably are thinking of it, oil and water. You put oil and water together, as long as you stir, sure, they'll stay all mixed up, but as soon as you stop, then they're going to fall apart. So let's talk about this dissolving process, okay? Dissolving, you're really talking about spreading something out evenly within another, okay? You're not doing a chemical bond here. You're actually taking the solute and you're spreading it out evenly in the solvent. So how do we speed it up? How do we make it faster? Well, there's two ways, and anybody that likes iced tea, especially sweet tea, knows this. Way number one is you can shake it or stir it. If you shake or stir something, it will dissolve faster because you are actually increasing the surface area contact between the solute and the solvent. Okay, you're making it so you're literally spreading the solute out and letting more of the water kind of get up there in the middle of it. The second way, this is a big one for you tea drinkers, is you can increase the temperature. Anybody that's ever tried to dissolve sugar in iced tea knows it takes forever. Hot tea is so much easier to dissolve. Why? Because an increased temperature means there's more energy, and that's more kinetic energy to get those particles moving and to spread them out. Now, temperature is a really interesting thing when it comes to solubility. And one of the things that you're going to have to be able to do on your SOL is you're going to have to read what's called a solubility curve. This is the solubility curve. Now, clearly, I screenshotted this off my iPad, so ignore the top. You've got a great one on your PowerPoint. You're going to get a worksheet in class. But what you're looking at here is a whole bunch of different substances. Okay, so you see all these different lines. This top one up here is potassium iodide. Then you've got NaNO3 right here. So they're all labeled, and they're looking at solubility. It's showing you at different temperatures, that's what's down on here on your x-axis, how many grams of the solute will dissolve in 100 grams of water. So a couple things you have to be able to do with this graph. The first one is straight up read it. All right, that's pretty simple. So if I asked you how much NaNO3 will dissolve in 100 grams of water at 10 degrees, you find the NaNO3 curve, okay, and that one happens to be fairly straight. Per 100 grams of water is what this graph is showing, and then I said 10 degrees. So we'd go to 10 degrees, and it would be that 80 grams of NaNO3 can dissolve in 100 grams of water, okay, at 10 degrees Celsius. That's what this graph is showing you. So other things you've got to be able to do besides just flat out reading it is you've got to be able to identify trends. Don't let this per 100 grams of water mess you up. Okay, the per 100 grams of water is just what's on this graph. We'll get more of that in a second. But you might be asked, what is the least or most soluble at a given temperature? Okay, for example, you might be asked, okay, what substance is the most soluble at 10 degrees? So I find 10 degrees, and the most soluble would be way up here, Ki. I can put like 138 grams of this stuff. The least soluble would be this KClO3 down here. I can only put like 5 grams in there. So when you're doing that, you're identifying trends. So that's one thing you may have to do. Another thing you may have to do, this is like one of my favorite words, you might have to extrapolate data. Tell me that's not the greatest word ever. Okay? Extrapolating data means you have to take it past what's on the graph. So let's say I ask you, how much, we'll do KClO3, this curve down here at the bottom. How much KClO3, okay, will dissolve in 200 grams of water, 200 grams of water at 50 degrees. Well, now I got to think a little bit. Okay, 50 degrees, KClO3, I got that. That's right there. Bam. So 20 grams of this stuff. But that's how much will go in 100 grams of water. So extrapolating data means I have to think, okay, so if 20 grams will go in 100 grams of water, and I have twice as much water, yes, you figured it out, you'll get twice as much of the solid. So if it's 20 grams, like I said, per 100, then this answer is going to be 40 grams. If I double the water, I double the solute. Okay? The only other thing I've seen asked from this solubility curve on your SOL is sometimes they'll ask you how much precipitate will be formed when you cool something from one temperature to another. For example, let's look at KNO3 because we got a little space. And let's say we're going to cool KNO3 from, I believe that's 60 degrees, pretend that dot's where it's supposed to be, down to 40 degrees. Okay, and we want to know how much solid's going to come out. Well, at 60 degrees, I had 100 grams of my powder. At 40 degrees, I had 60. So how much solid is going to come out when I go from here to here? It's just 100 minus 60. That's going to be 40 grams. So you're going to have a worksheet you're doing in class practicing. Don't let this graph intimidate you. It's actually really, really, really simple. Okay? Speaking of simple, here's another simple concept. Another simple concept is saturation. Believe it or not, there is a maximum amount of solute that can be dissolved. I told you that before. That is called a saturated solution. Okay? You're holding as much as you possibly can. If you have less than that amount, it's called an unsaturated solution. And then there's my favorite. if you play around with temperature and pressure and some other factors, it's actually possible to get more than the maximum amount. Okay, this takes a little bit of chemical fooling, but it's totally doable. And if you get more than you're supposed to, wait for it, it's called a supersaturated solution. Okay, I don't know why it makes me happy, it just does. So those are other words you need to be familiar with. Beautiful. All right, last but not least, we are going to talk colligative properties. And again, I hope you're in class for this because this is the ice cream you get to make. Colligative properties are pretty cool. They are any physical effect the solute has on the solvent. So it's not specific to the solute present. It means it doesn't matter what you put in, it's the fact that you're putting something in, and it's really dependent on the amount of the solute. Okay, so again, you've got this all in your PowerPoint. It's totally worth checking out, but colligative property is what is the solute doing to the solvent. And the really nifty thing, I think, is it's not necessarily about what the solute is. So there's actually several of these colligative properties. We are going to very briefly talk about two. We're going to talk about boiling point elevation, and then we're going to talk about freezing point depression. Okay, so freeze point depression. So let's start with boiling. Okay, these are colligative properties. So if we talk about boiling, all right, now this one always cracks me up. A lot of you guys, I know add salt to the water when you cook, like when you make pasta. And if I ask you why you do it, you might say, oh, it makes the water boil faster, or oh, it makes the pasta cook better. Most of the time, the reason we do it is because we saw our mom or our dad or our grandma do it. I'm not going to lie, that's totally why I do it. The reality is that somebody told me once it made the water boil faster. That's a blatant lie. What you've got to remember is water boils, okay, and you know this already, when your vapor pressure is equal to your atmospheric pressure. All right, we learned that in the last unit. So if I add salt to the water, okay, so here's my big old pot, there's my water. When I put salt in it, the salt is actually blocking the collisions between the water. Okay, when I look at total volume here, it's really less water. And there's less collisions between the water especially. And because there's less collisions between the water, there's actually less vapor pressure in that water. So because there's less vapor pressure, it actually takes more energy and thus a higher temperature to get that to boil. So it really actually does not boil faster. In fact, it actually takes longer to boil. It boils more slowly because it has to get to a higher temperature in order to boil. Now, most of us do not put enough salt in the water to make a difference. We like sprinkle it in and think we're doing something. If you ever watch chefs, man, they put some salt in there. But you're still only raising this boiling point from, say, 100 degrees Fahrenheit or Celsius, maybe to, 103. Ooh. But if you're a chef, okay, that higher temperature can actually give you more efficient cooking, more even cooking, because you're going to maintain it better with the whole evaporation of the water. And a lot of chefs really, really think you get a better product that way. But the fascinating thing is it wouldn't have to be salt. Okay, if you add any solute to water, you are going to see boiling point elevation. In theory, you could put sugar in the water. You could put alcohol in the water. It's going to still cause that boiling point to go up. So let's look at the flip side. The flip side is where our ice cream lab came in. That's our freezing. Okay, so again, a lot of people are familiar with this. You live in Draft, you are used to seeing salt on the roads. Okay, a lot of people think salt, oh yeah, it's going to keep it from sticking on the roads, or it's going to melt the ice. Well, some of that's right. The thing to remember is that when water freezes, okay, it forms crystals. So in order for water to freeze, the two molecules have to come together, and you actually have to have two Mickey Mouse heads connected. Okay, that's going to be how you form a crystal. Well, if I put ice in, the ice actually breaks down into sodium and chloride ions. Those ions actually block the crystal formation. They literally get in here and they get in the way. So because they're getting in the way, it's actually going to take more energy and therefore a greater temperature change, stick with me on this, in order to push them out of the way so the water can actually crystallize. That means it actually has to be colder in order to freeze. Okay? It's got to be colder because otherwise I've got to take more energy away. I'm going to have a big temperature change in order to pull those suckers out of the way. So go back to the salt on the roads thing and think about it. When do we put salt on the road? We don't put it after it started snowing. We don't put it when the roads are wet. You usually put salt down before the storm. Think about those stripes. The reason they put it down is when the snow hits and it melts, the salt will mix in with the snow and hopefully keep it from refreezing on the roads. Now, if it's -4 like it was some this past summer, salt isn't going to do anything. But if you're hovering right around that freezing point, the salt can actually make it where it would have to be even colder than freezing for that water to refreeze and keep our roads safe so you can come to school and learn chemistry. If you have any questions, you know where to find me.